All right. So section 9.4. We've got a couple of new theorems. Theorem 9.8 and theorem 9.9. 9.8 is the 45 degree, 45 degree, 90 degree triangle theorem. Remember it either way. And it says that in a 45 degree, 90 degree triangle, the hypotenuse is square root of 2 times the longest leg. Not longest leg, times the length of a leg, sorry. Like they're the same length. Times square root of 2 times the length of a leg. So we call the legs the ones that aren't the hypotenuse, right? And in the 45, 45, 90 triangle, it looks like this. And so the two legs are the same length. And so basically you could write that triangle with this being 90 degrees right here. This is 45, and this is 45. And you could say that these values are x, and this value here is square root of 2x. Okay? Now, have you guys seen this special triangle before? Did you see it in Algebra 1? No, probably not. All right. It's not going to go away. I'm using this in pre-calc, right? And I mean, I just think in my mind, I think when I have a 45, 45, 90 triangle, the values here are 1, and this value here is square root of 2. And so it should make sense that you'd still have the same triangle if you multiplied any of those values by the same number, right? So you can adjust the size of it, but this is like the smallest version of it. It helps me remember those numbers. So always remember 1 square root of 2. Same thing with a 30, 60, 90 triangle, which is our other theorem. So theorem 9.9, 30, 60, 90 triangle theorem. And that says in a 30, 60, 90 triangle, the measurements are, and this one you just have to draw the triangle, make it simpler. So we have a 30 degree angle here, 90 degree angle, a 60 degree angle there, and those values are x, 2x, and square root of 3x. And again, just to kind of point this out, the way that I was taught to remember this was, 30, 60, 90, and you remember 1, 2, square root of 3. All right, so either way that's simplest for you to remember is fine. But this is kind of like that triangle in its simplest form, and then you can multiply it by any factor and get bigger or smaller triangles. If the x was a fraction or a decimal, then it would be a smaller triangle. All right, so they give us, I'll let you guys finish writing that down, and then we'll do example number 1. I'm going to write that on the board. So what kind of triangle? You guys, everybody done writing? What kind of triangle is this? As far as our special triangles go?
It is a 45, 45, 90.
How did you know that though? Because we don't have a 45 listed here. So can you say that?
Well, because 90 plus
Now?
40.
Yes, because they have to add it to 180 degrees.
They have to add it to 180. So that one's got to be 45. So Mill, Cameron, and Cal. I was just trying to think, is there any way I can link all of you guys together?
You just do
What if I
CA.
say CA cubed? How about that? Huh? All
Is there
right.
another CA?
Nice. Okay. So this is a 45, 45, 90 triangle, right? So what we have over here will hold true. I can say then that the length of any side, that the hypotenuse, right, will equal square root of 2 times the length of any side times the leg, right? And so in this case here, hypotenuse is represented by an x, and we know the length of each of the legs to be 3, and so our final answer would be 3 square root of 2 would be the value for the length of the hypotenuse. Did I lose anybody when I did that? Does that make sense? Do I got that? The next problem's just as simple, but here they make the length of the sides to be x, and they make the length of the hypotenuse to be 5. So again, we can say that the hypotenuse is square root of 2 times the leg, but we're given the hypotenuse this time, and square root of 2 times x is the value for the length of one of the legs. And so in this one here, we would divide both sides by square root of 2, and we would say x equals 5 over square root of 2. Don't like you to leave a radical in the bottom there. So how would I simplify that guy? Write that a little clearer. Don't like square root of 2 in the denominator. Don't like a radical there, so I want to get rid of the radical in the denominator. I would do what? Jackson.
Multiply the top and the bottom by square root of 2.
That's right. So multiply bottom and top by square root of 2. Because if I multiply it by square root of 2 over square root of 2, I'm really just multiplying it by 1, so I'm not changing the value of that, right? And so on the top here, I get 5 square root of 2. And what's square root of 2 times square root of 2? It's just 2, right? When you multiply something under a square root times itself, it drops the radical. So you could, think of it as this, square root of 2 squared. Raising a radical to the power that's of the same degree basically undoes it the way that multiplication undoes division, and addition undoes subtraction, and so forth. All right? So square root of 2 times square root of 2 is 2. All right, let's try a 30, 60, 90 triangle problem. So we're given this triangle here, 30, 60, 90. Again, they could have just given us one of those. They could have just said 30 and the 90-degree part there. We would have known that it was a 30, 60, 90. And they labeled this as 5. They labeled this as S, and they labeled this as T. And they want us to find those values. So for this triangle, we can say that the hypotenuse, which is t, we know that 2x equals square root of 3x. Everybody agree with that? I'm sorry, that's not right. So don't agree with that. Let me do that again, sorry. All right, we know that the 5 equals square root of 3x. Let me say that. Right? Does everybody agree with that? All right, so then I can find, this is using my special triangle right here. I can find the value of x to be x equals 5 over square root of 3. I'm just going to leave that as that for right now. We're going to see how it works out. If this was something I was having to give an answer for, I'd get rid of that radical. But I'm going to leave it like it is for now and see what we get in the end. So now that I've found out x, I know from the way this one's drawn, based on this triangle here, I know that t equals 2x, right? Because t is my hypotenuse. My hypotenuse here is 2x. And so then I can say that t equals 2 times 5 square root of 3. That's going to give me 10 over square root of 3. And sure enough, I've got a radical on the bottom, so I'm going to multiply top and bottom times the square root of 3. And so I'm going to get 10 square root of 3 over 3 as my answer for t. This brings up an important point on the test that I just handed out. My geometry class is exploding next year. So I've already got like, I don't know, 30-something students, and I'm going to have to open up a second class. And so I realized that I'm not going to be able to grade all these tests unless I do as many multiple choice problems as possible. So your current test, most of the questions are multiple choice. So I'm going to try to do, you can clap. Don't make me turn red, all right? So I say all that to say is one of the things I've told you in the past is make sure you circle your problem. But now that's going to be a lot simpler for me because you're going to circle A, B, C, or D, right? But yeah, if I don't give you multiple choice, make sure you circle your answer so that I know which one was your final answer. Does everybody see how I got that for T? Does that make sense? I'm just kind of plugging in those values. Yes. For X, for S, I don't really have to do anything, right? Because in this particular triangle, S equals X. So that means that S equals 5 over square root of 3. I do need to get rid of the radical, so I'm going to multiply top and bottom times square root of 3 again to get 5 square root of 3 over 3. So that's my value for S. Okay, any questions about any of those? I think we should do a word problem. I think we have time. Just because word problems, for whatever reason, you guys, if something's described in a word problem, you just immediately assume this is super hard compared to all other problems, right? And they're not always. You just have to make sure that you can take your job is to take the word problem, the way that it's described, and turn it into something that's like this, right? So let's see if we can do that for one of our problems. Let's jump to the road sign one. That's a cool one. So I'll leave all that up there so we can reuse it. So they tell us that we've got this yield sign. Let's talk about yield signs for a moment, okay? If I come up to an intersection and I didn't draw that very well, but you guys know. You guys have seen these, right? How many of you guys in here have either your learner's permit or your driver's license? All of you? Okay, almost. Okay, almost all of you. All right. Let's talk about yield signs for a moment. All right. Let's make sure that we're all on the same page there.
I didn't know we driver's ed.
All right. So, particularly because now this wasn't the case when I was a kid, but or a young adult, as you guys are. But when you would come up to a red light, and I'm not, in South Georgia, we would just say red light referring to a traffic light, but I mean a light that's actually red, right? And you want to make a right turn. The rule is, if you're making a right turn on a red, you have to do what first?
Yield.
Wait, I didn't know
You have to slow down.
You have to
No,
stop.
wait, what?
You have to stop. You can do that.
What?
You have to stop.
You have to stop completely
Oh.
unless one of these signs are there, okay? They've got these signs all over the place now, but if they don't have that sign there, you have to come to a complete stop before you make a right turn, all right?
It's
One example of that is where the Sam's Club is in Sharpsburg, which is near where I live. If you're coming towards Peachtree City, and I'm sitting like in front of the sands, that car washes over to my left, and I come to that red light, if it's red, and I have to come to a complete stop before I can turn right because they don't have one of these signs there. All right? And so what that means is that if someone is, if someone's coming from this direction and they're taking a left in there, I have to stop and they have to come through, right? So, I mean, you're yielding to, even if there was a yield sign there, I would have to yield to that traffic. But I'm trying to think, where is it where this is such a problem? Here's where it's a problem. It's actually more of a problem when someone's coming from the Peachtree City area and to somewhere that's got a yield sign like this. So where's an example of that? There's a yield sign. Where's there a yield sign? I picked the wrong intersection. Most other intersections have a yield sign.
Yeah.
Okay? So if I'm coming from the opposite direction and I want to go here, let's draw this out. All right? This is important. All right? This is going to save your life one day. All right? Here's the road. All right, here we are coming here. There we go. There we go. All right, you're coming along, and we've got a little box here, and then of course in Peachtree City, there's other signs that don't block the box,
Yes.
or will destroy you. Right? So I'm coming this way. All right, I'm coming this way, and someone's coming this way, and they have a yield sign. Right? And I'm coming this way and I want to take a left. Okay? So if they have a yield sign there, they have to yield to me. Right? But sometimes, I'm confusing myself now and where this is important. But there's been too many times where people assume there's a yield sign there and there's not a yield sign, right?
Or they just straight up run red lights.
So this is the main thing I want to stress. If there's not a yield sign, you have to come to a complete stop.
So you're going like with a light, and what you're saying is that some people like there's not a yield sign there and they try to go, but you have the right of way because you have the turn lane. Is that what you're saying?
I'm trying to say that I have the light. Maybe the problem is with this car here, right? This car here treats it like a yield sign. They go ahead and go, but like Mary said, you have to come to a complete stop, right? And so I've got the right of way here, and they don't yield, so they like run into me or try to run into me, right? So if you have a yield sign, you have to wait for this guy to come. And sometimes this is on Highway 74. If I'm taking a right on Highway 74, there's no yield sign right there. So I've been coming from my house to Highway 74 and wanting to take a right down there by where the Chipotle is and the Starbucks and all that kind of stuff. And people are honking at me because I come to a complete stop because, like Mary said, I'm obeying the law. The light's red, and I'm supposed to come to a complete stop. And they're laying down on their horn because I came to a complete stop and didn't keep going. I can't keep going. There's not a yield sign there and my light's red. And there are cops like sitting around that intersection all the time. So I'm going to come to a complete stop, and I'm not going to block the box. Right? Okay. So either I saved your life or I saved you from a ticket. Okay, so one or the other. All right, but we have a yield sign, and they draw a little. We just need to take the yield sign and realize.
Before we
See,
I know, I got this.
you guys are getting your money's worth
I'll
today.
be ready in 2 years.
Yep.
So-
2 years you'll be like, so walking.
So it says, estimate the area of the sign by finding the area of the equilateral triangle. And they actually draw this picture for us. They say this is 18 inches, and this is 36 inches. And so we need to figure out what the height is. And they tell us we're going to divide this up into a 30, 60, 90 triangle. So this is 30, and this is 60, and this is 90. How did I know which one was 30 and which one was 60? Yes?
If they all add up to 180, then each would be 60, and since you've split it with a bisector, each on that bottom side would be 30.
Each of the bottom side would be 30, yes. So I can think about it like that, like Aiden said. Since they already gave me the the sides, like he said, they're equal. So we know they're 60 all the way around. I've got a bisector here, so it's going to divide it into 30. Also, another way to check yourself if you ever have a problem like this, the shorter side has to go with the shorter angle. The side that's across from that angle has to be shorter than this one here, because this is across from the 90-degree angle. So this has got to be the bigger number of the two. So that's something else that you can look for as well. All right, but we're trying to find h. And so now we've got this 30, 60, 90 triangle. We need h because we use that in order to find the area of the triangle, right? So h is going to be, based on our diagram right here, h corresponds to which value? X square root of 3x or 2x? I don't hear anything.
Square root of 3x.
Square root of 3x, thank you. So h equals square root of 3x. What is x in our diagram?
18 inches.
X is 18 inches, right? So it's this side right here. X equals 18 inches. That corresponds to that. This would be our 2x side, right? So that means that square root of 3 times 18 is what h is, or we would write that, we normally write the number in the front and the radical afterwards, right? So 18 square root of 3 inches is the unit for the height. And then I know that the area then is equal to 1/2 the base times the height. What is the length of our base? The way that we've drawn this triangle? Our base is this side here.
18.
So it's 18 times 2, right? So it would be 36. Right? The length of all of these sides are the same on our yield sign here, so it would be 36. So base is 36 times our height, which is 18 square root of 3. So who said 30? No, someone said 18. They didn't say 36. Who said 18? Gabe said 18. You see why it would be 36, Gabe? All right. You broke the silence, though. Okay, there was this awkward moment. I was trying to figure out what I'm going to do now, right? So thank you for breaking the silence. And that would be a big number. We punch all that in, and we get 561.18. Is that our answer? Awkward silence again.
Inches squared.
Inches squared, that's right. We've got to have our units, right? So our unit there would be inches squared. Don't forget your units. Okay, let's move on. And I got to make sure I don't derail and talk about any other traffic issues because we don't have time. Let's do, where am I? There we go. Trigonometric ratios. Ooh, these are fun.
Oh boy.
They sound fun.
All right. Have you guys been introduced to any trig functions before?
Nope.
Okay, Brittany says yes. Not that you know of. Was it in Algebra 1?
No, I took pre-calc last year.
You took pre-calc already? Where were you? Where did you see it, Jackson?
I took a SAT prep course.
SAT
I
prep.
had to learn a bunch of this.
Gotcha. Okay. Well, this is pretty cool that I get to be the first one to introduce many of you guys to trig functions. That's pretty cool. I got to write that down in my scrapbook.
Take a picture.
Yeah, right. All right, so let's trigonometric ratios. I'm going to abbreviate that and just say trig ratios.
Trig rat.
And trig rat, yeah, I could do that. So if ABC is a right triangle, if triangle ABC is a right triangle, the sine, cosine, and tangent are, and sine, cosine, and tangent are all trig functions. All you really have to know for this class is what they equal. So I'm going to draw my right triangle here. A, B, C. That's what I'm going to label the points as, the vertices as. And then for the side opposite that vertex, I'm going to do a little version, a lowercase version of the same letter. So we got a C, a B, and an A like this. And so sine of A is equal to the length of the opposite side over the hypotenuse. So in our diagram here, what variable have I labeled the hypotenuse as?
C. Little c.
Little c, right? So this is our hypotenuse. So sine of A equals opposite over hypotenuse, or A over C, over little c. Because the side is opposite big A is little a, and the hypotenuse is little c. The cosine of A is equal to the adjacent side, the side that it's touching, which is not the hypotenuse, which in this case is B, over the hypotenuse, which in our diagram is C. And then the tangent of A is equal to the opposite side from A over the adjacent, the length of the adjacent side. So in other words, little a over little b. That's the tangent. So there are two ways to remember this that I've learned. The way that I don't like is this old, ancient Native American word, Sakatoa. You have to say it like that. Sakatoa. Sakatoa.
Okay.
Oh, wow.
That's one of the ways that I learned it when I was in school. The reason I don't like this is because I never could remember when you say Sakatoa, it's like, well, sometimes an A makes an ah sound, and so I guess you have to say so-ka-toa. So if you really make sure you hit the so-ka-toa. I never could remember if it was Sakatoa or Sokatoa or whatever, right? So I like to remember it like this. And where does that come from? Sine is opposite over hypotenuse. You see that? Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. If that works for you, great. Like Jackson said, you'll see this on SAT, and so it's important that you remember the relationship of these. What I learned that stuck with me better is, saddle, it was like a Western thing. Saddle our horses, right? What do those horses do? They canter along happily. And then since we're all on our horses, cantering along, it's two other adventures. And see, that's just corny enough that you remember it for the rest of your life. And to this day, I was once sitting right where you are, around your age, and I've never forgotten saddle our horses, canter along happily, two other adventures. Whichever you prefer, right? I know I've got some horse people in here, so I figured you would like this one better. All right. But either way works, just whatever way you want to remember it. And you're like, I don't have to remember anyway, I will have a note card. But you won't have a note card on the SAT. Right? So you need to memorize this. You need to know this. It reminds me of an interesting traffic incident, so I want to talk about that. All right, so let's find the sine and cosine. Which one do I want to do here? So we're told here that they've labeled these A, B, and C. Let's don't do that one. Let's do example 2. All right, so for example 2, we have a triangle that looks like this. So these don't have to be any of our special triangles, right? It just has to be a right triangle. And for this right triangle, we're told that the length of the sides are 5, 12, and 13. And they say, find the sine, cosine, and the tangent of the indicated angle. They label the angles as this. right? Now, which length corresponds to our hypotenuse for this triangle?
13.
13. How did she know it was 13?
Because that's the hypotenuse.
Because that's the hypotenuse. Okay. Can somebody give me a more logical answer? Yes, Joshua? It's the longest of the lengths, so that's one way that you can think about it. It will always be the longest in a right triangle, or you can think of it, yes, Paul?
It's across from the right angle.
It's the side that's across from the right, so opposite the right angle, right? That will always be the hypotenuse. So either of those methods will help you track the hypotenuse down, okay? Once you know the hypotenuse, then the opposite and the adjacent stuff will vary depending on which angle you're looking at, whether you're looking at angle R or angle S, okay? But in our case, we're trying to find the, for angle S, we want to find the sine, the cosine, and the tangent, all right? So let's see if we can do that. The sine of S, angle S, is going to equal, sine corresponds to opposite over hypotenuse. So what's the length of the side that's opposite angle S?
Opposite of angle S.
When we say opposite, we're looking at angle S here, and we basically drawing an arrow
5.
to the side that's opposite that, so it's 5, okay? So it would be 5 over hypotenuse, which is 13. So that would be the sine of S. The cosine of S is the adjacent side over the hypotenuse. The adjacent side is the side that's touching angle S, but isn't the hypotenuse, so it would be this side here. So that would be 12 over 13. And then the tangent of angle S would be the opposite side. Let me write that down. Opposite over adjacent. So it would be 5 over 12. That would be the tangent of this. And you can punch those in your calculator and you can get a decimal answer if that's what they asked for. Like I said, if you see this on a test in the future, it'll probably be multiple choice answers. So if it's in decimal form, then you'll just need to punch it in on your calculator to get the decimal. So that was all of those values for angle S, but what about angle R? Let's find the same thing for angle R. So sine of R, cosine of R, and tangent of R. What does sine equal?
Opposite over hypotenuse.
That's right. Saddle our horses. So opposite over hypotenuse. The opposite side for R, we're looking here. So opposite side for R is 12. The hypotenuse is still 13. Cosine is canter along happily or caw, right? Cosine is adjacent over hypotenuse, and so the adjacent side to R is 5 over 13. And what's the tangent for R? Tangent corresponds to two other adventures, so what? Tangent equals opposite over adjacent, good. And so the tangent, the opposite side to R is 12 over the adjacent side, which is 5. And again, you can punch those in your calculator and you could get a decimal answer. Interestingly, something that you may notice here, I don't think they make a big deal about that in this, but notice that if for the two other angles that are in a right triangle that aren't the 90-degree angle, the tangent of one will be the inverse of the tangent of the other, and whatever the sine of one is will be the cosine of the other, and vice versa. Cosine of that one is the sine of that one, so it'll always work out like that. All right, so example 3, they ask us to find those same things for a 45 triangle. So this is where, remembering it like I showed you right here, is going to be helpful. So if we have a 45 triangle, and they ask us to find the sine, cosine, and tangent of a 45 triangle, they don't have to specify which angle, because the other angles, the angles that aren't the 90-degree angles, are identical, right? So I remember this as 1 square root of 2. And so when I find the sine of a 45 triangle, we'll just label, it doesn't matter, we'll label this angle A down here. The sine of angle A is going to be what?
Over hypotenuse.
Opposite over hypotenuse, so 1 over square root of 2. So we multiply top and bottom by the square root of 2 to get rid of that radical on the bottom, and so we get square root of 2 over 2 is the sine. For a 45 triangle, the cosine of the angle is going to be exactly the same, because when I take the adjacent, since the length of the adjacent side is the same as the length of the opposite side, adjacent over hypotenuse is also going to be 1 over square root of 2, so it's going to be square root of 2 over 2. And then when I take the tangent of a 45, 90 triangle, it's the opposite side, which is 1, over the adjacent side, which is also 1, so the tangent is just 1. All right, any questions about either of those? Is that pretty simple?
Yeah, it's a brain workout.
The brain workout? That's right. We're here to think, not here to snooze. All right, contrary to what some of you guys think.
My brain is like,
All right, you're working out. That's right. You guys are getting the big head as well. Big brain. You guys are like Mega Mind,
Oh yeah.
right? Or the guy, and you guys seen Sky High?
yeah.
The guy that's like the chemistry teacher in Sky High. I love the part when they're like, somebody talking about somebody leaving their lights on, and he's like, excuse me, you know, my bad. You know, and like walking out. I don't know. He just cracks me up. Or when he's the little baby guy.
I haven't seen that movie.
Oh, the baby guy's actually the funny part. Where the bad, who's the tough guy in the movie, and he's got to reverse the what was the weapon of destruction called?
Something that the girl has a.
She like turns them into babies, and the guy with the big head says that he can fix it, but when the guy that could throw the fire picks him up, he says, "Regrettably, I've made boom boom." You guys remember? All right. Anyway,
God help me. Like,
pretty fun.
like, I used to.
So that's really all that's in here, right? There are some word problems where you can estimate. We got 5 more minutes, so let's do one more. Let's do estimating the distance, which is the escalator problem, example number 7. All right? Mr. Pease, that's it. Mr. Pease. I can be of assistance. All right.
I need to watch that video.
It's not Pease, I guess it's Peace, Mr. Peace. Warren Peace, I think it's his name.
Yeah.
So we've got this triangle here.
Weird name.
30 degrees and 76 feet and some distance d. And so the way that they set this problem up for us is they say the escalator at the Wilshire, Vermont Metro Rail Station in Los Angeles rises 76 feet at a 30-degree angle. To find the distance d a person travels on the escalator stairs, you can write a trigonometric ratio that involves the hypotenuse and the known leg length of 76 feet. All right. So this is our escalator. It's too bad we don't know. I wonder if it's not. So I used to work in CNN Center, and CNN Center has used to have the longest freestanding escalator. I don't know if it still does or not, but it's like it's not supported by anything except for the point at the bottom and the point at the top.
Scary.
So yeah. So I wonder, it's too bad I don't know what the degree is here, and then we can maybe calculate that. So it'd be something a little closer to home. But anyway, we can figure this out, right? We can figure out d easily. This is just one of our problems using the trig ratios. We just have to determine which trigonometric function am I going to use to calculate that?
30, 60, 90.
It's a 30, 60, 90 triangle that I'm using. You're right about that. But which of these trig functions here are going to apply? Which trig function, in other words, relates this angle 30 degrees to this value of 76 and this value of d? Aiden.
Sine.
Sine. So Aiden says that sine, because sine is the opposite over the hypotenuse, and this is my hypotenuse, that those are related. Does everybody see that? So that's true. So we could say that the sine of 30 degrees is equal to 76 over d, opposite over hypotenuse. All right? Here's where it gets fun. And you guys have to know how to use your calculator. What was required in this class was that you have a scientific calculator, and this is one of the reasons why, because scientific calculators will have the trig functions on it, right? So you could punch in sine of 30 degrees at this point, and if you punch in sine of 30 degrees, you will get 1 over 2 or 0.5, right? You get 0.5, and that's because I remember this triangle here, right? Sine of 30 is opposite over hypotenuse, which is 1/2. So this is 0.5 equals 76 over d. And so I would multiply both sides by d here, get rid of this d here. So 0.5d equals 76, and divide both sides by 0.5. And if I divide 76 by 0.5, I get 152. Is that right? Yes? All right, so 152 what?
Units.
Feet.
Not feet. There we go. Yeah, we had some units to start with. So that would be our answer for the length of the escalator. So make sure that you know that you can punch this in your calculator, and you can actually calculate the sine or the cosine using your calculator. Okay? All right, you guys have a good day. Let you out a few minutes early. You're welcome. Man, that's nothing great.